All right, guys, let's see if we can wrap up this conjugated diene chapter here on a Saturday afternoon. Let's get this video done, and that way we can kind of move on and be ready to go with some practice the next time we meet, and then move on into aromatic compounds after that. Uh, One of the things that we need to get finished is Diels Alder reactions. Then we need to do Cope rearrangements, and we need to do Claisen condensations. By far, most of the video today will be discussing Diels Alder reactions because there's a lot of different things to consider when it comes to a Diels Alder reaction. Cope rearrangements are fairly straightforward. We're going to just talk about whether or not we're going to produce a more substituted alkene product. That's really going to be the driving thing to look at. And then Claisen condensations are going to be a little bit of a challenge because at the end of the day, you might have to rearrange it so that it's in the correct shape or that it's in a familiar shape in order to do the mechanism for the rearrangement to see the product. And so I know there's a lot of stuff going on in organic. It's a lot of work, and you just got to stick with it. So once I get this video posted, hopefully you'll be looking at it, and we'll be able to do some practice right away on the next time we meet. So let's get going. Let me start my screen here. All right, see that where we left off last time. Okay, let's see what's going on here. All right, so what's a Diels Alder reaction? A Diels Alder reaction is where we take this thing over here, a diene, and we react it with something that has a double bond, and this is a dienophile. And it reacts in a way to form a six-membered ring with one double bond. And so if we think about it from the perspective of thermodynamics, we're going from two sigma bonds, three pi bonds to one pi bond. We are creating two new sigma bonds. And so at the end of the day, the reactants are lower energy than the products. And so that's going to be a negative delta H. What about delta S? Are we increasing the entropy or decreasing the entropy? Well, we should remember that we're decreasing the entropy because we're going from two things to one. So if we think about Gibbs free energy being delta H minus T delta S, with this being negative and this being negative, that ultimately the negative term becomes positive, so you get a negative and a positive. Well, we need to keep the temperature fairly low in order to, and not cold, but we need to keep it lower in order to keep this reaction moving in the spontaneous direction. In other words, keeping the equilibrium, favoring the closing of the ring rather than the opening of the ring. So these reactions happen, at room temperature up to about 200 degrees. And then after that, the reverse reaction starts to be favored. And so really it is an equilibrium, and at high temperatures, really high temperatures, the retro Diels Alder reaction is what's favored. Okay, and so this reaction doesn't proceed too fast. The yields are pretty low, but it can be sped up if the dienophile has an electron withdrawing group attached to it. And now electron withdrawing groups are one that you can show by resonance withdraws electrons, and I'll show you one example of this. Here would be the resonance structure showing a withdrawal of electrons. What other groups could be electron withdrawing groups? So this proceeds faster with an electron withdrawing group, and it could be R, where R is CH. Well, R is a C group or a hydrogen group. It could be OR, where R is a C group or a hydrogen group, or it could even be, it could be a nitrile group. That's also a possibility. It could be better if it were, there we go, like that. So these are the type of electron withdrawing groups that you'll see, and this is what makes Diels Alder's reactions be quite product favored. And so typically what you'll see is some electron withdrawing group. Okay, so let's take a look at this though. There's some considerations to be made when we think about these Diels Alder reactions. Again, it's a dienophile reacting with a diene to form a 6-membered ring from 2 different products. So what happens though if you take a diene and you react it with a dienophile that's cis? There is a particular stereochemical outcome that we have to consider. And so in this case, the 2 groups, and I'll show the mechanism again, just to make sure that we're all on the same page here. The 2 groups will point in the same direction. If it's trans, then a different stereochemical outcome is produced. The groups go in opposite directions. And in this case, you would have an enantiomer. All right, and so there's one thing that I want to make sure that I say. This diene just has no reaction. And so the diene must be, it must be S cis. It can't be S trans. Okay, so when you think about Diels Alder reactions, consider the dienophile, and if there are multiple electron withdrawing groups or multiple groups on the dienophile, consider whether or not you can label it as cis or trans in order to decide what kind of product that you'll get when it comes to stereochemical orientation. Now, you can do Diels Alder reactions with alkynes as well as alkenes. There is a slightly different result. The mechanism is still the same, but notice I have a total of 3 bonds, 2 pi bonds there. I'm only breaking one of the pi bonds to make a sigma bond, so I'm still going to be left with 2 pi bonds at the end of the day. And now when it comes to this thing, you really don't have to worry about stereochemistry over with these groups, because remember, you're forming an sp2 hybridized carbon. That's going to be planar, so you don't have to worry about whether or not it's up or down. So let's do a quick example real quick, just so we can kind of sort this out. Let's do one where we have our diene, and let's do this one where it's CN. What's the product of this one? So what are we going to consider? Well, we could remind ourselves of what the mechanism is. That's one thing we could do to help us remember what the product is. And then we can also say to ourselves that the dienophile is trans, and so product is trans. In other words, we're going to have to deal with two different enantiomers. And so if I draw the six-membered ring that's formed, I'll have one that goes up, one that goes down, and now all I have to do is put the other groups there. And to be perfectly accurate, we would say enantiomer. All right, now in this case, it's symmetrical, and so we don't really have to deal with an enantiomer unless I do something like this. All right, so just keep that in mind. Keep that in mind for a stereochemical outcome. Let's do another one. What about a dienophile that looks like this? Here's a good old carboxylic acid group. And then let's make the diene look like this. What's the product here? Just draw the mechanism again to remind myself. Probably won't do that anymore. Now, this is cis, so that means that in the product, these two groups will point the same direction. So it's a carboxylic acid group. Okay, so that takes care of that. One last example. Let's do it where we have a, let's go ahead and add CH3 here. Let's add a CH3 there. Let's do a triple bond where we have a ester, an ester group here. So we're still going to have the same basic product. I'm going to have some CH3s right here. And then I'm going to have a double bond here. And I'm still going to have the ester group here. Okay. So what we did is we introduced the Diels Alder reaction. We talked about the mechanism. We talked about that you really need an electron withdrawing group in order to make it move in the forward direction and produce any appreciable amount of products. Then we talked about the differences in cis and trans dienophiles, talking about whether or not they would produce six-membered rings where the side of the six-membered ring would be would have bonds where the groups that are attached to the were attached to the dienophile are pointing in the same direction or they're pointing in the opposite direction. So this is really a stereochemical outcome discussion. We talked about what happens if the dienophile is a triple bond. Really, then the stereochemistry part isn't a concern, but we do have a different, a little bit different of a product that's formed with two double bonds instead of one double bond. Okay, there is some pretty interesting situations with Diels Alder reactions, though, that can go on, and that's that the diene can be a ring. Now, remember that the diene has to be locked in the S-cis position, and so rings meet that requirement, and so oftentimes we show a six-membered ring and a five-membered ring as being the dienes. And so what happens in this case is that you still form a six-membered ring. And the problem is if I draw it like this, then what's happening to the other part of the ring, the five-membered ring that's not involved in the mechanism? And so the mechanism involves this ring formation. So what's happening with that? Well, it's still there, and we could show it like this. The problem with this picture, with this version, is that it's going to be a little bit more of a challenge to deal with some of the stereochemistry. So what I want to do is, instead of showing it like that, I want to show you how to draw a little bit better of a picture, a little bit better of a perspective on that six-membered ring. So you actually draw this sort of slanted, this chevron slanted at an angle. And this way we can show that five-membered, again, here is the five-membered ring that was already in existence. And now we're creating, here's the new sigma bonds that we created that came from here and here. Now, that makes it a little bit easier if we have to get into a situation, which we absolutely will in just a second, if we have to show some groups that are attached at that location. And so we'll deal with that in a second, but let me show you how to do this next picture. If your diene is a six-membered ring, then you still have the same sort of chevron. So I'm going to draw this tilted chevron here. It's just a little bit tilted. But instead of a point, it's a square, sort of a square. And so here's the bonds that were already in existence. There they are. They're still there. And here's my new from 1, 2, 3. Here's the new sigma bonds that are made from the dienophile. Okay, hoping everything's picking up on the mic okay. I think it is. This mic's pretty sensitive. So I'm talking a little slower today because it's Saturday and I'm a little bit tired. I've been working all week, but I want to make sure to get this stuff taken care of for you. Okay, and so what about this? Let's get to the same, do the same thing, and let's add some groups to it though. Let's make it a little bit more complicated. What if we do this? What if we have this cyclopentene, or the cyclopentadiene, and we react it with this guy. What happens in this case? So let's draw our chevron. Let's draw the pentagon. And in this case, I have one group that goes up and one group that goes down. And so the bonds in this position is a little bit different than the bonds that would be in a cyclohexane because of the other groups that are attached to it. So they both go, so there's two bonds that would be sort of described as axial if you were to use your language from cyclohexane chair conformations, and they're right next to each other. And so that's a little, and they're axial and they're pointing down, they're pointing the same direction. And so that's a little different than we would expect if we were to see it from the perspective of a cyclohexane chair conformation. But it turns out there really is a preference. So if I were to do the same reaction, but with a cis dienophile, then now won't I actually have two possible outcomes? Two possible outcomes? Well, there's still two possible outcomes here where the R groups could be switched around, but that's not what I'm talking about. I'm talking about this. Let's see, so let's make them cis. So now what I'm getting at is that one version looks like this, where the R groups point the same direction, up, and another version is like this, where the R groups point the same direction but down. This one is called exo, and this one is called endo. And it turns out there really is a preference. It turns out that this endo product is the major product. It also turns out that steric hindrance isn't the explanation. Now, when it's exo, it's endo, it's whether or not the groups point sort of in the same direction as the additional bridge or in the opposite direction as the other bridge. That's where the endo and exo come from. And if you were to think about it that way, then you might say, well, maybe this is the one. Well, this one might not be preferred because there could be some steric hindrance happening with those groups. But at the same time, you might say, well, isn't there some sort of strain happening there as well, using what we learned from cyclohexane chair conformations? And what we get into is we get into sort of a weak explanation because there isn't a whole lot of evidence that we can develop for this unless we do some sort of quantum mechanical simulation, or well, we know that the endo product is favored. So we, just like before, when we know that something is favored, forms faster, then we know that it is actually a lower transition state. And so now we're stuck with trying to explain why is it a lower transition state. And so what we explain is that at the end of the day, there is a favorable interaction that happens. So one of two things can occur. One way is that the diene could line up, and what I want to do is I want to flip this on its side. So let's see if I can draw a slightly better, a little bit more of a projected version of it. So this one is coming towards me, and I could take this dienophile, and these R groups could be pointing away. Or I could take the same dienophile. Let's see if I can do this one here. Pointing towards me. Shade it in here. Now I can have these R groups pointing back towards the ring. And what we're saying is that the reason why there is a stabilization in this direction that leads to a lower energy transition state that makes their to give the endo preference is that there's some sort of electronic interaction that's happening with the electrons in the R groups. And so that's really all that this particular textbook has to say about it. We know from experiment that the endo product is favored. We know based on the examination that you and I just did that, well, there's some sterics going on that way, but there's also some sterics going on that way. So maybe it's something more than that. And so here's what we're going to offer for you. And if we get into some quantum mechanical calculations, we might be able to actually see those things. What happens if we get a cyclopentadiene and we react it with another cyclopentadiene? But in this case, the cyclopentadiene is also the dienophile. And so I'm going to get the same result. I'm still going to make a 6-membered ring. Draw it down here. Draw my little chevron. Formed this thing. But what's attached to the rest of that structure where the new bonds are in purple? Here's my new bonds. What's attached to the rest of this structure that's already there? Well, I've got another 5-membered ring. And remember, there's going to be an endo preference. So it must actually be pointing somewhat down like this. Try to still make it a 5-membered ring. And then remember, where was the double bond? If this is where the double bond was that made the new sigma bond, and this must be where the old double bond was that's still in that location. All right, and so when we think about it, as long as there's some sort of so this is just the very first part, and this covers a lot of information when it comes to Diels Alder reactions. So again, we've talked about the diene, the dienophile, how to make the dienophile a little bit more reactive by adding electron withdrawing groups. Talked about what happens if the dienophile is actually an alkyne. We talked about the stereochemistry, extensively talked about the stereochemistry, even bringing up this idea that the stereochemical product has could have an endo or exo preference if the dienophile is trans, or excuse me, is cis. If it's trans, remember, we'll just, one is up, one is down, and it could be both versions of it. We can swap those two positions. But now remember, there's other things besides stereochemistry. There's regioselectivity. And so let me give you an example of regioselectivity when it comes to Diels Alder reactions. And so we don't have to worry about regioselectivity if there's lots of symmetry going on. So if there's symmetry in the diene, I'm only going to get one version of the molecule, right? I'm only going to get one version of the molecule. So if I do that, it's going to be the same. The R group is still going to be connected 1, 2 spots away from the double bond. So if there's symmetry in the dienophile, then we still get sort of the same regioselective consideration. Now, remember, I'm not talking about stereochemistry. I acknowledge that there's differences in stereochemistry, but I'm specifically talking about regiochemistry here. So, prime and R prime. So there's definitely differences in regiochem, or in this case, there's still the same situation as far as regiochemistry is concerned. The R prime is connected 1, 2 away from there, and I've got another R prime connected 1, 2 away from that spot. So the connectivities are the same. Of course, again, we know that the stereochemistry is going to be different. Okay, let's take a look at another situation. You know, if it's an alkyne, we get pretty much the same thing going on
as long as there's symmetry in the alkyne. The connectivity will be the same. The difference comes in is when there's not symmetry, or when there's a lack of symmetry in both molecules. Let's take a look at this one as an example. Let's make this one an ether. And let's make the dienophile unsymmetrical as well. Make it a carboxyl. Oh, I'm going to actually just make it an aldehyde so I don't have to draw as much. So now there's two possibilities, right? And that when I say two possibilities, I mean two possibilities for the regioselective outcome. One regioselective outcome is where the two groups are close together. And the other regioselective outcome is where the two groups are far apart or further apart along the ring. So which one is it? Which one is it? Which one? Which one is major? Okay, this is where we're going to have to use some of our resonance skills and determining resonance structures. And what you'll see is there's going to be an electrostatic reasoning, an electrostatic reason why one molecule might orient in a particular way as it relates to the other molecule. With the electron withdrawing, and the other one happens to be electron donating, with the electron withdrawing and donating groups, there's clearly some resonance going on. And so let me show you the resonance. So let's draw some resonance. In this structure, you could have the electrons here move out to the end of the atom, the end of the diene, and I could have a resonance structure that looks like this. There's a positive charge here and a negative charge there. Let's see about the resonance in this structure. This one is electron withdrawing, and you can see that through resonance. When we say electron donating and electron withdrawing, we typically mean through resonance. Could be through induction as well. But in this case, we're talking about resonance. So let's draw the resonance structure with this one. What do we got? Look what's going on here. Here I've got a positive charge, and here I've got a negative charge. If these things are moving around in solution, then remember that the real molecule does definitely exhibit some partial charge characteristics at the locations where there's full charges shown in a resonance structure. So there really is some partial positive charge at this location and some partial negative charge at this location. There really is some partial negative charge at this location and some partial positive charge at this location. Well, then what that means is that there's going to be a preference for how these things want to line up with each other. If I project the diene in the same direction, then there's a preference for them to line up so that these two charges are interacting in a way that provides a little bit more stability for those partial charges, right? So a partial negative charge will be attracted to a partial net positive charge, just like any other situation when there's some polarity that's going on. And so we can orient them this way, and we can continue to show our excuse me, we can show the mechanism. It's a little bit more complicated to show it with this particular picture. But it can be done. And we get back to our 6-membered ring. And, you know, I'm not doing a really good job of showing that hydrogen there, showing that hydrogen there. It's still there. And this guy is an OCH3 like this. And so it turns out that this one is the major product and this one is the minor product for that reason. Okay, so what that means is that as a student doing Diels Alder reactions on systems that are unsymmetrical in both the diene and the dienophile, then there's going to be a consideration to be made when it comes to choose the major product. The consideration that you'll need to make is, are there some partial positive charges that I have to think about in order to line up the molecule in the correct direction with some other partial negative charges? Thinking, of course, that the partial negative charges will want to line up with the partial positive charges, and that's what will lead to the major product. Okay, I hope that's fairly straightforward for you, because at the end of the day, that's the last complication that we have for Diels Alder reactions. The next thing that we want to go into in this video to help knock out the rest of this section is the cope rearrangement. And so there's not much really that's going on with the cope rearrangement. You can find out how we refer to these as when we think about them in terms of their transition states. I don't think it's a particularly important discussion to have at this moment. The language of the particular reaction being a cope rearrangement is fine with me. So look what happens. There's no net change in the number of sigma bonds or the number of pi bonds. It's just a difference in where they are, okay? And so one might even say that there's no reaction here because it's the same molecule, essentially. This is where we have to deal with some differences with a cope rearrangement. Why might this one be driven forward this direction? Let's think about it. If I'm going to have this same mechanism take place, then what do I end up with in the products? In the products, I end up with a situation where I have a more substituted alkene versus so this one is disubstituted, this one is monosubstituted, and in this case, they're both monosubstituted. So we know that this one's thermodynamically more stable. And this is really the major considerations with cope rearrangements. When you're presented with a reaction that's a cope rearrangement, then the driving force for all of them is that we're going to form a more substituted alkene. And that's it. That's it for cope rearrangements. The next bit that we want to get to, and it's the last bit, is the Claisen Condensation. And the Claisen condensation is not as much to think about when it comes to a Diels Alder reaction. In fact, it's analogous to the Cope rearrangement as far as the mechanism is concerned. But it's just a little bit of a difference in the driver. In this case, I still haven't picked up that red marker yet. There we go. In this case, I form a doubly bound oxygen. And what we say is that a doubly bound oxygen is more stable than a doubly bound carbon. And so again, the thermodynamic driver is that it's more stable in the product. So it's the same mechanism as Cope rearrangement. It's a similar reasoning when it comes to driving the reaction forward. But in this case specifically, it's creating a doubly bound oxygen from a doubly bound carbon, and that's more stable. Okay, when do we see these reactions? And so how do you identify this? Well, it comes when there is a vinyl and allylic ether at the same time. And so remember, vinyl means one, or it means directly attached to the double bond, and allylic means one removed from the double bond. And so it's when you have this situation. So this is the simplest version of it. This could be an R group here. This could be an R group here. There could be other R groups along the chain. And that's when things really get complicated. Now, it could also happen with vinyl and aryl. So with allylic and aryl. So it could be aryl, remember, is directly attached to a benzene ring, so it could be like this. So this is aryl allylic. And again, there can be some different things that are attached to these molecules. And what's difficult is that when we think about the Claisen condensation, we picture it this way so that we can think about the mechanism. But oftentimes we might be presented with a molecule in that projection. So for instance, what if I showed you something like this? Let's add a methyl group here. Let's add an ether here, double bond here. And then let's take some methyl groups all around here. How do I produce the product in this case? Well, the first thing that I want to do is I want to arrange it so that it's shaped like this molecule. I want to put the projection in the correct location so that I can look at it like this, and then once I look at it like that, then I can do the mechanism without any problems. And so it's okay if I just sort of start out with drawing my oxygen in one location. And then think about what this side is. This is the vinyl side, and this is the allylic side. This is the allylic side. And so let's just draw it like that so that it's correct. Here's the vinyl side here, and here's the allylic side here. Okay, so I want to draw that allylic business like this. And it just takes a little bit of practice, and you can sort this out with a little bit of practice too. And what goes right here then? There's a CH3 there. Okay, now let's take a look. How do I get this vinyl side correct? Well, it's going to go up, and then there's going to be the double bond immediately. And what's attached to that double bond? Well, I've got a CH3 here, a CH3 here, and a CH3 here. This is just a CH2. Now that I've done this, I can do my mechanism. Remember that this one's going to come down here. This one's going to come here, and that one's going to come there. And this way I can now write the product. So the product will involve this doubly bound oxygen bound to a carbon that has a CH3 here. What functional group did I create? It seems like I created an ketone. Okay. Looks like this one actually is going to be tetrahedral now. So maybe I want to make sure to leave some room to show that. But now I'm going to be, that's my new sigma bond. Here's the new double bond. And then there was a CH3 right there. And so this is still the same CH2. This is still the same CH2 that was there to begin with. And so here's the product of this Claisen condensation. And so again, it's not too difficult when it comes to the mechanism or to the basic idea of how to draw the products involved. But there is some challenge when it comes to arranging them so that you can draw those products in a familiar way. What you're going to have to be able to do is identify situations where you have allylic and vinylic ethers together and then rearrange them appropriately. Now, remember that it can also work with aryl and allylic ethers. And so we can have that situation. And so there is a little bit of a challenge there. Oops, that's a little too big. Because the product distribution isn't quite the same. So here's the situation where we've got allylic and aryl. Now, we still want to rearrange it so that these double bonds are in this general projection. And so that's going to be a challenge. So let's go ahead and let's try that now. So I'm going to zoom this up to the corner, switch that out. So let's try that. And so this one seems to be already in mostly the correct orientation. So let's go ahead and draw that double bond there. Well, that is where it'll be. But I'm going to finish drawing the benzene ring. Okay, so that's the double bond I'm thinking of. That means that these are where the other double bonds are. And then to that is connected that oxygen. And now let's put the rest of this allylic group back in this position. Okay, there we go. Now we have it. Now we have it. And so now I can see the outcome of the reaction. I'm going to form a bond there. Oh, I'm doing this backwards. Thank you. It's going to come there. It's going to come there. And it's going to come there. Now, this is what we end up with. We end up with this situation where we have a benzene ring from the reactants that is now no longer a benzene ring. It's got this situation going on. And so if you remember from alkynes, there's actually a situation where there could be tautomerization. And that's exactly what's going to happen. The subject in the middle is not actually isolated. What we get is actually the enol, and the reason we get the enol is because we restore the aromaticity. And you can show the mechanism of tautomerization any way you like, whether it's acid catalyzed or base catalyzed. It's going to depend on what else is going on in there. But typically I'm not going to need to see the mechanism, but remember you do have to know the mechanism of tautomerization. So if you don't remember what it is, then go back to that alkyne chapter and take a look at that. And so this is actually the product, because while some of these steps are definitely reversible, this one isn't really appreciably reversible. And so that's it with Claisen condensation. That's all the major considerations to make. And so again, what did we do? We reviewed Diels Alder. We talked a lot about Diels Alder. So there's a lot of stuff going on with that, from stereochemistry to regioselectivity to having bicyclic compounds being formed as a product, then thinking about endo preferences and exo preferences. It was an endo preference, of course, in that case. Then we moved on to well, what about the regioselective outcome? You know, if there's not symmetry in one of them and no symmetry anywhere, then was it like this or was it like that? How do we know? We have to look at the resonance structures. Then we talked about the co-rearrangement, which was fairly straightforward. It's just going to be dictating the product is going to be the one that creates the more substituted alkene. And then we talked about Claisen condensation. And Claisen condensation was essentially the same mechanism, but it involved aryl allylic ethers or vinyl allylic ethers. And the challenge that we had with that was to project the reactants in the way that we learn the mechanism so that we can take a look at that. And so at the end of the day, that's all that's going on with that. And what this does is this really does conclude everything from the conjugated dienes chapter, because what comes next is aromatic compounds. And we'll spend some time talking about aromatic compounds and what's aromatic and what's not aromatic, and think a little bit about the molecular orbital theory of those aromatic compounds. But ultimately what we're going to get into is electrophilic aromatic substitution. And there's a lot to talk about in that bit of organic chemistry. And so that's the next big challenge for organic chemistry too. All right, guys, signing off. See you later.